So, good afternoon, good evening, good morning, everyone. Our topic for today is rules of inference. Rules. It is presented by Muhammad Zaidon and Edolmero Reyes. So, let's go to the first topic. Conjunctive addition. Conjunctive addition refers to the use of conjunctive adverbs to connect two independent clauses or sentences. These adverbs help show the relationship between the clauses by adding information, emphasizing a point, or introducing an additional idea. So, these adverbs though help show the relationship between the clauses, two sentences or two independent clauses. So, let's go to the example. So, we got here, we're using the adverb, conjunctive adverb, moreover. So, the first sentence is the presentation was well organized. What is well organized? The presentation. Let's go to the second sentence. The visuals were compelling. What was compelling? The visuals. So let's read it again. The presentation was well organized. Moreover, the visuals were compelling. So what is the sentences wants to prove? Let's go here. It is emphasizing a point and introducing an additional idea. So the first idea was that the presentation was well organized. Then because of the conjunctive adverb moreover, we got more information that the visuals were also compelling. So wow, the presenters really did well on their presentation. So let's go to the second example using the adverb furthermore. She aced the written exam. Furthermore, her oral presentation was outstanding. So, by reading the two sentences added by the adverb furthermore, we got the idea that the girl was really smart and very excellent because she aced the exam and also her oral presentation was also outstanding. Do you get the point? That's just the point of the conjunctive addition. It's just to connect the two ideas. Okay? Let's go to the conjunctive dilemma. Oh, dilemma. So here, we got here the definition. Conjunctive dilemma occurs when a person faces a difficult choice between two equally undesirable options. It's a situation where both alternatives have negative consequences. So, can you really make a choice when it's both negative consequences? So, let's go to the example. So, we got here the example of the sentence. Jane had to choose between attending her best friend's wedding or an important work conference. So, we got here the sentence or the scenario 1. Jane had to choose between attending her best friend's wedding or an important work conference. So, in the first sentence, if she choose that option, if she attended the wedding, she'd miss the conference. Here, she'd miss that important work. So, and if she attended the conference, she'd miss the wedding. So, it was a conjunctive dilemma. So, we can say that it is a win-win because if you choose the other option, you will miss the another option, another opportunity like that. So there's no a good choice, but it is to choose what's the best for you at that situation. So let's go here at the scenario number 2. Mark was torn between accepting a job offer in a different city or staying in his current job. So we got here the explanation. So if Mark accept the job offer in a different city, so which would mean leaving his family, or stay in his current job, so which had limited growth or limited growth opportunity, both options had downsides, creating a conjunctive dilemma. So do you now get the point of the conjunctive dilemma? It is a difficult choice between two equally undesirable options. It's a situation where both alternatives had negative consequence. So That's it. It's very simple. We will know it is a conjunctive dilemma when the two sentences are have both negative consequence. So that's it for the resolution. So here, resolution is a significant rule of inference in propositional and first order logic. First order logic is a method for proving the unsatisfiability of a set of clauses and is used in automated theorem proving. In the context of rules of inference, resolution can be seen as a generalization of the modus ponens rules. So, for the example, Edelmero Reyes will take over and explain it to you guys. So, that's it for me. Bye.
Example: it is either raining or it is cold. It is not raining or I will wear a coat. So the given P and Q, it is raining or it is cold. Given number 2 would be negate P and R, it is not raining or I will wear a coat. The resolution would be combine this to get Q and R, it is cold or I will wear a coat. Example 2. I will go to the gym or I will study. I will not go to the gym or I will watch TV. Given 1, A and B, I will go to the gym or I will study. The given 2 is negate A and C. I will not go to the gym or I will watch TV. The resolution would be combine this to get B and C. I will study or I will watch TV. Direct proof. A direct proof is a method of providing mathematical statements by directly applying definitions, axioms, and previously proven theorems in a logical sequence. The aim is to show the conclusion necessarily flows from the given premises without assuming anything other than what is already established. Examples: prove the sum of two even numbers is even. So this is the proof. Let A and B be two even numbers. By definitions of even numbers, A with a value of 2k and B with a value of 2m, for some integers k and m, their sum is A plus B is equals to 2k plus 2m equals to 2, open parenthesis k plus m, close. Since k plus m is an integer, 2, open parenthesis k plus m, close, is even. Thus, the sum of two even numbers is even. Example number 2. Prove if n is an odd integer, then 2n is odd. This would be the proof. Assume n is an odd integer. By definition, n is equals to 2k plus 1 for some integer k. Squaring n gives 2 equals to, open parenthesis, 2k plus 1, close, 2 is equals to 4k, 2 plus 4k plus 1. This can be written as 2, open parenthesis, 2k plus 2, 2k, close, plus 1, which is clearly of the form 2m plus 1, an odd number. Thus, 2n is odd. Indirect proof. Indirect proof, or proof by contradiction, involves demonstrating the truth of a proposition by showing that assuming the opposite or negation leads to a logical contradiction. This contradiction implies that the original assumption must be false, thus proving the original proposition true. Example number 1. The sum of an irrational number and a rational number is irrational. Assume the sum of an irrational number is A and a rational number B is rational. Therefore, A plus B is equals to Y, where is Y is rational. Rearrange this to A is equals to Y minus b. Since y and b are both rational, y minus b is also rational. The difference of two rational numbers is rational. This implies that a is rational, which contradicts the initial statement that a is irrational. The conclusion would be therefore the sum of an irrational number and a rational number must be irrational. Example number 2. There are infinitely many prime numbers. Assume that there are infinitely many prime numbers. List these prime numbers as p1, p2, p3, so on until pn. Consider the number p is equals to p1, p2, p3, so on, pn plus 1. P is either a prime number itself or it is not. If P is a prime number, it is not in our list of primes, which contradicts our assumption that we have listed all primes. If P is not a prime, it must be divisible by some prime. However, when dividing P by any prime pi, the remainder is 1, since P is equals to K pi plus 1. Therefore, P cannot be divisible by any prime numbers in our list, which is another contradiction. Conclusion, thus, the assumption that there are finitely many prime numbers must be false and there must be infinitely many prime numbers. That would be all. Thank you for listening.